Today's video lesson, we're going to talk all about the least squares regression line, what it is, how it works, why it's useful, and how we can find it using either a graphing calculator or using a spreadsheet program like Google Sheets, Excel, and etc. Okay, so to start off with, the general form of a regression line is that y hat. So we've seen this before with p hat. So when you've got that caret above the variable, we call that hat. So y hat is equal to a plus bx. This is not the way you're probably used to seeing linear equations. You're probably more used to this second form over here on the right-hand side. There's nothing wrong with that form. It's just not the one that we typically use. We typically use this form, which sometimes makes more sense because you start with your y-intercept, which is kind of the starting point, and then you go up by your slope. So it gives you a more kind of clear picture about how the graph works that we probably should use more often. But just a reminder, the constant that does not have a variable attached to it, in this case, a is always going to be your y-intercept, and then the coefficient of x, the number in front of x, is going to be your slope. So let's talk about the difference between y and y hat. Why are we using y hat instead of just using y? And in this case, it's because y is actually going to represent the observed value, whereas y hat is going to be the predicted value. In other words, looking at your data, the y values are the actual values that you observed in the data. So it's not really fair to call it y equals a plus bx. It's better to use y hat. Now the inputs are still going to be the same, so x doesn't need to change, but the outputs are not going to be observed values, at least for the most part. They're going to be predicted values. And there is a difference there. In fact, section 6.3 with residuals is going to take a little bit closer look at the difference between how close your observed value and predicted value match one another. So let's take a look at an example of this. So don't you hate it when that can of soda that you're going to open opens and all the contents start spraying out and you have to run to the sink or grab towels to clean it up? Well, there were two stats students, Carrie and Danielle, who wanted to investigate if tapping on a can of soda would reduce the amount of soda that was expelled after the can had been shaken or dropped. Obviously, this is something that you probably have seen people do. They'll tap on their soda can to try to release some of that pressure. For their experiment, they vigorously shook 40 cans of soda and then randomly assigned each can to be tapped for either 0 seconds, 4 seconds, 8 seconds, or 12 seconds. Then, after opening the can and cleaning up all the mess, of course, the students measured the amount of soda that was left in the can. We don't have the scatter plot. I should have taken that out. But we do have the least squares regression line, which is that soda hat is equal to 248.6 plus 2.63 multiplied by tapping time. Now, you'll notice that rather than using x and y, they're actually using the variables from the prompt or from the context. And that's a pretty common thing to do. In fact, if you don't use those variables, if you choose to use x and y, you need to make sure you define what x and y represent in your equation. Obviously, they did not do that. They went ahead and used the actual variables themselves, so there's no need to define your variables. In this case, they are already self-explanatory. So what we're going to do first is we're going to identify and interpret both the slope and y-intercept. Let's start with the slope. So the slope is going to be whatever is the coefficient for our variable. Obviously, tapping time is our variable, and this positive 2.63 is in front of it. So that 2.63, and usually with slope, we want to think about that as a fraction. So to make it a fraction, we'll just put it over 1, so 2.63 over 1. So we would say for each additional 1 second of tapping time, so for each 1 second of tapping time, that the amount of soda in the can is going to increase by about 2.63, and it was in terms of milliliters. So every second you tap the can, you can expect a little bit more than 2.5 milliliters to still be left in the can. So the longer you tap the can for, it looks like the more soda is going to be in the can. Let's also talk about the y-intercept. So the y-intercept is the constant. whatever number is not attached to a variable. So that would be this 248.6. So as a point, that would be at 0 and 248.6. So what we would say is a can that was tapped for 0 seconds, or you could also write that as at the beginning or without tapping on the can, should have about 248.6 milliliters of soda inside of it. Okay, so when you're interpreting for the slope, you're saying for each increase in your explanatory variable, so for each 1 second increase of tapping time, that our response variable, the amount of soda left in the can, should increase by whatever number is in front of your variable. Obviously, if it's a negative, then you would instead say that it would decrease. As for the y-intercept, that's always going to be your starting point, your beginning point. So without tapping the can, or a can that has been tapped for no time or 0 seconds, we would expect to have 248.6 milliliters of soda inside of it. Okay, so now let's talk about how to use that regression equation. So again, we've got that soda hat is equal to 248.6 plus 2.63 multiplied by the tapping time. And what we want to find in part B is to find the amount of soda that's remaining for a can that's been tapped for 10 seconds. So we're going to put 10 seconds in for our tapping time. So our amount of soda that we predict in the can, so soda hat, is going to be equal to 248.6 plus 2.63 multiplied by tapping time. So let's go ahead and put that into our calculator. We're going to have 248.6 plus 2.63 multiplied by 10. And that's going to tell us that we would expect for there to be about 274.9 milliliters of soda left in the can. All right. For example C, predict the amount remaining for a can that has been tapped for 60 seconds, and how confident are we in that prediction? Before we do that, let me go ahead real quick and close out of OneNote since it is freezing up. Give me just 1 second here, and we'll be back to it. Okay, cool. So again, that amount was 274.9. Let me go ahead and write that back in for us here on OneNote. Maybe we'll see. We'll try one more time here. There we go. Cool. Write that a little bit smaller. So 274.9 milliliters are left in the can. And again, we got that, our soda hat, by taking 248.6 plus 2.63 multiplied by 10, and then there was our answer. So now we're going to do the same thing, but we're going to do it for a can that's been tapped for 60 seconds. So we're going to use the exact same equation. So we're going to say that soda hat is equal to 248.6 plus 2.63, but this time multiplied by 60. So if you were to tap it for a full minute, let's see how much soda we would expect to have in the can. So if you hit second enter on your graphing calculator, then you can just move over and change the 1 to a 6. That'll save you a little bit of time. Otherwise, you would have to type all that back in. But it looks like we would expect for there to be about 406.4 milliliters of soda left in the can. Now, how confident are we in this prediction? Well, how much soda actually fits in a can? Let's go figure that out. How much soda is in a can? All right, and in terms of milliliters, it looks like that a 12 fluid ounce soda can contains 354.82 milliliters. But somehow our can of soda has more than that. It has 406.4 milliliters. So not very confident in this case. And the reason for that is that 60 seconds is outside of our given inputs. Keep in mind our inputs for our number of seconds were told that they were tapped for either 0, 4, 8, or 12. So basically everything from 0 up to 12 we would be okay with. In fact, in part B, when we tap the can for 10 seconds is between 0 and 12. So we can be pretty confident that our prediction in part B is pretty accurate. But for C, that's not the case. 60 seconds is way outside of 0 to 12, and in fact, our answer was more than what should have been in the can in the first place. So this is the idea of what is called extrapolation. So extrapolation is when you use a prediction equation outside the given interval of inputs, your outputs are not going to be accurate. So we're going to take a look at one more example of this, and then we should be kind of done for today's video. So in this next example, Sarah's parents were concerned that she seemed a little bit short for her age. So their doctor had the following record of Sarah's height. So the first row was age in months, whereas the second row was the height in centimeters. So in this case, our explanatory is going to be the age, and our response is going to be the height. Obviously, you would expect for the height to be determined by how old they are, at least at the early stages that she's in. Probably not going to determine their age based on their height. That would especially be a problem if there was an older age, because you kind of don't really change a lot in height once you reach a certain age. So it definitely makes more sense for X to be age and Y to be height. So let's go ahead and make a scatter plot of this data. Let's first do it using our graphing calculator, and then I'll show you how to do it once again using Excel, in this case using Google Sheets. So the first thing you're going to need to do is go to Stat, choose the option for Edit, and then make sure that all of your data gets put into List 1 and List 2. So List 1 is going to be all of your inputs, so the age in months, so 36, 48, and so on, all the way up to 60. And for List 2, 86, 90, and so on, up to 95. So we're going to go to first y equals, make sure that everything is cleared out of that, and it is. Then we'll go to second y equals to go to our stats plots menu and make sure that we have one of those turned on. We'll go ahead and turn plot number 1 on. For type, make sure it's scatter plot, and then make sure that for X list and Y list that those say list 1 and list 2. Once you've done that, we're going to go ahead and press zoom and choose option number 9 for zoom stat, and we should be able to see our scatter plot. So we're going to make just a simple sketch of that. So here is a sketch of what that looks like. Pretty linear data, really, if you take a look at it. So linear model, hopefully it's going to be a pretty good fit. But let me go ahead and draw this in. 1, 2, and then 3. And then let's make sure we label our axes correctly. Remember, the x-axis was our age in months, and we'll get our numerical labels in just a moment from the calculator. And then we had also our y-axis was height, and that was in terms of centimeters. Okay, for numerical labels, remember to just press window and copy down what it has for the x min and max and y min and max, so 33.6 up to 62.4. And then for y min, that's going from 84.47 up to 96.53. Next, in part B, we're going to go ahead and use our calculator to find the equation of our least squares regression line of height versus age. And we're going to add this to our scatter plot that's above. Okay, so let's go ahead and talk about how to find that regression equation first. So we're going to go to Stat, over to Calc, and we're going to do linear regression, and we're going to choose option 8 for a plus bx. If you wanted to choose option 4, that's also linear regression. That's just ax plus b, which is the second form that I mentioned to you. They're both okay. I'm just going to use option 8 for a plus bx. Once I'm in there, we're going to have x list as list 1, y list is list 2. For frequency list, we'll leave that blank. We are going to talk a little bit more about storing the regression equation a little bit later on, and then we'll go ahead and hit calculate. So we're given some information. Yours might not have r squared and r, and if they don't, that's okay. We'll talk a little bit later on about how to get those. But at the very least, you should have a and b. Notice that a is 71.95, so that's going to be the y-intercept, and then b is 0.383 repeating. That's going to be our y-intercept for b. So we're going to write this in as our equation. We'll use this form right here first, and we'll talk about what we need to do to define some variables. But we'll say that y hat is equal to 71.95 plus 0.383. And that's being multiplied by x. Now, we need to define what y and x are. We can do that a couple different ways. We can just kind of write out that y hat represents the predicted height, and then say that x represents the age in months, and I'm using this part right up here to say that. So x is the age, again in months. The other thing we could do is just simply rewrite our equation and say that height hat is equal to 71.95 plus 0.383 multiplied by, in parentheses, age. So you can either define your variables once you've written your equation down, or you can just replace the variables in your equation with the actual variables themselves. Now let's just think about what that means. Our y-intercept is 71.95. That would mean that at an age of 0, so when the baby was born, when Sarah was born, she would have been about 71.95 centimeters. Now how accurate that is, we don't know. We do know that the slope is that on average for every additional month that we expect her to grow by about 0.383 centimeters. So let's do this. Let's use our regression equation first to predict, well, let's see. I think there was a second part. We wanted to add this to our scatter plot. So we want to add this equation in to be able to see our line of best fit. In order to do that, you've got kind of a couple different options. If you have the menu like mine, it'll be pretty easy. If not, we'll show you kind of how to work it. So we're going to go back over to calc. We're going to go back to this option 8 for linear regression a plus bx. And in that menu, in addition to list 1 and list 2, we're going to store our regression equation. In order to store it, we're going to pick out a variable to store it as. So we're going to go to vars. And then we're going to move over to yvars for y variables. The first option for function will let you choose y1. We're going to select that. So now what's going to happen is it's going to store that regression equation for us into y1. Alternatively, you could just go into y equals and type it in. That would be kind of another thing if you didn't want to go through the trouble of storing it. But storing it's going to make it a little bit more accurate. Notice that it's going to give you the same screen right here, but when you press y equals, you should now see that equation in there. Now, if you did not have the menu pop up, then after linear regression shows up on your home screen. So let me go to the catalog and we'll find that option to kind of show you how this will work. But what you should see on your home screen if you don't have the menu is just something that says linear regression a plus bx, and it's flashing like this. What you'll need to do is specify list 1, so second 1 is your inputs, comma, second 2, list 2 is your outputs, comma, and then you'll go ahead and find the y variables, so vars, yvars, function, option 1, and when you press enter, it should end up doing the same thing as what we had. You'll get the same values, and now you should also see that equation showing up in your y equals. Now when we press graph, in addition to our data, we will also see our line of best fit going through those points. And again, it's linear, so a pretty easy one to draw in. I'll try my best to do this on my computer here. So not perfect. In fact, one of those points, it looks like, should be below, and one should be above. So let's make it a little bit more accurate here with that line of best fit. Okay, so one above, and then the other one was somewhere below. Okay, cool. So now we're going to use our regression line to predict Sarah's height at 40 years, which is at 480 months. And then we'll convert that to inches by using this conversion rate, which is 2.54 centimeters, being equal to 1 inch. Now again, keep in mind we're doing this for 40 years, so quite a bit is going to be different from what we would expect based on our regression line. Let's go ahead and plug in that 480, which is the number of months that is, and see what that gives us as an output. Probably the easiest way to do that on your graphing calculator, if you hit trace, arrow down to your regression line, then what you can do once you're tracing on that is just type in the number that you want to go to. So in this case, 480. Ooh, and it's outside the window, so that's not going to work. Darn it. We'll actually just have to type this one in. That's okay. So we'll go 71.95 plus 0.383 multiplied by 480. And that tells us that they would be a height, Sarah would be a height of 255.79 centimeters. To convert that to inches, we're to take 255.79 and divide that by 2.54. So let's go ahead and do that. Divide by 2.54. So that would be that Sarah is going to be 100.70 inches tall, which, yeah, in part D, it's impossibly large. Think about how many feet that is. To divide by 12, that would be 8.4 feet tall. Not to say that it can't happen, but not very likely that she's going to be 8.4 feet tall. So explain why this happened. Well, this is an example of extrapolation. All right. Very last thing that we're going to talk about is what's called the coefficient of determination, which is r squared. This is the fraction of the variable or variation in the values of y, which is accounted for by the least squares regression line. That's the technical definition. The easy way to think about it, though, in parentheses, it's how well your model fits the data. So how well does our linear model fit the data? Now, just like r, the closer to 1 it is, the better the model. Closer to 0, the worse the model. So when you calculate it, we're just going to use your calculator to find r and then square it. Some people will already have r squared given to them on their calculator, which is great. So about the interpretation then is that about blank percent of the variation in response variable is accounted for by the least squares regression line or by the linear model. It's really just kind of a fill in the blank sentence. You really just copy the sentence down, plug in the number for r, and you're done. So how is r squared related to r? Both measure the fit of the data. Both are measures of fit. However, r describes the association, whereas r squared describes the linear model. So the difference between the two, r is just looking at the points, r squared is more focused on the line. So we're going to find the coefficient of determination, r squared, for the example above, using our graphing calculator, and then we'll interpret it. If you did not already have r or r squared show up, you're going to need to change an option in your mode. So go ahead and press mode, and then you're going to scroll down to an option that will be called stat diagnostics. And you need to make sure that that is turned on. So mine is already good to go. Yours will probably say off if you didn't see it before, and just make sure that that gets turned to on. If you do not have that option, so if you have an older calculator like a TI-83, instead what you'll need to do is find it in the catalog. So second 0, go to option D for diagnostic, and then you'll have to scroll down through the D's until you find one that'll be called diagnostic on. So there's diagnostic off. Here's diagnostic on. Go ahead and select it. Press enter. It'll tell you done. And then you've got your calculator ready to go as well. Once you've done that, we're just going to go back into stat, over to calc, choose that option once again for linear regression, a plus bx. Again, you can leave all that as it was. And now when you run your diagnostic, you're going to see both r squared and r, at the very least one or the other, and you can always use one to find the other. So our coefficient of determination, r squared, for our particular problem that we were just working on is 0.988, or let's see, 0.98, let's get that right. Here we go. So 988. We'll just do 4 decimal places there for r squared. So pretty good fit. Again, closer to 1 the better, and this is about as close as you can get. Notice that r is also very, very close to 1, so very linear association to the data. So for our interpretation now, the only thing we have left to do is write out that sentence describing our association. So we would say that about, well, really 99% of the variation in the response variable, which was the heights, so in the heights is going to be accounted for by the linear model. All right, so that's all I had to share with you guys today. Let me real quick remind you about how to find all that using Google Sheets as well. I've already got all of that data in here. If not, make sure you open up a Google Sheet or wherever you're planning to work it and get all that data in. Again, I like to include the labels at the top because those make nicer labels on the graph as well. We're going to go ahead and highlight that, press Insert, and choose the option for Chart, and you should be able to see a scatter plot of your data. Now this scatter plot obviously looks a little bit different than the one we saw on our graphing calculator. Notice that it's keeping the graph from being truncated, which is okay. We're going to go ahead and find the line of best fit then. So we're going to go over to Customize, choose the option for Series, go down and choose the option for Trend Line. Once we've done that, we're going to choose what type. Obviously, we want it to be linear. Unless it's pretty clearly something else, we'll pretty much always use linear. For label, we'll choose that to be use equation. So there is the equation, and again, you see that very close to what we had for ours, just rounded a little bit. But yeah, 0.383x multiplied by x plus 72. And then we can also have it show our r squared value, which again, you notice is the same as what we found on our graphing calculator. All right, guys, that is all I've got for us today. Have a good rest of your day, and I will talk to you again next time.